So, pump is a mechanical operation device that, through mechanical motion, typically transform liquid or gases or slurries from electricity to hydraulic energy. In terms of the way the pump transfers the water, direct loading, displacement, and momentum pumps may be separated into three broad categories. Pumps work by any typically alternating or rotating process, utilizing energy to conduct the flow of fluid by motion. Pumps are regulated through several energy sources, from microscopic for use in medical application to massive industrial pump like manual controls, electricity, motor or wind power. Centrifugal pumps are machines used for moving liquid by converting dynamic rotational energy into hydraulic fluid energy. The turning energy produced usually an electric motor or a steam turbine if the feed water pump is powered by generator. Centrifugal pumps are used in more industrial application than any other form of engine. The volute pump is the most powerful centrifugal engine. In the volute of pump, fluid enter the pump axially through the eyes of the impeller, low pressure area, which the rotates at high speed. As the impeller and the blade rotate, they transfers momentum to incoming fluid. The fluid accelerates radially outward from the pump chasing, and the vacuum is created at the impeller eyes that continuously draws more fluid into the pump. As the fluid's velocity increases, its kinetic energy increases. Fluid of high kinetic energy is forced out of the impeller area and enter the volute. In the volute, the fluid flow through the continuously increasing cross-sectional area, where the kinetic energy is converted into fluid pressure according to the Bernoulli's principle. The impeller blades are usually backward curved, but there are also radial and forward curved blade design. The output pressure slightly changes according to the design used. The blades may be open or closed. Also, the diffuser may be fitted with fixed vane to help guide the flow toward the exit. The energy transferred to the liquid corresponds to the velocity at the edge of impeller. The faster the impeller revolves or the bigger the impeller is, the higher velocity head be.
And now, in this slide, I will present about Euler turbo machine equation. From the previous slide, that we already know about the introduction of centrifugal pump. So in this slide, I will talk about Euler turbo machine equation, or sometimes called Euler pump equation. It plays as a central role in the turbo machinery as it connects to specific work Y and the geometry and velocity in the impeller. The equation is based on the concept of conservation of angular moment and conservation of energy. For the left side of this slide, we can see the formula for the Euler turbo machine equation. So for the sharp torque, T sharp equal by rho Q bracket R2 V T2 minus R1 V T1. So for the second formula is water horsepower is PW equal ohm dot T sharp equal rho Q bracket U2 VT2 minus U1 VT1. And for the last formula is pump head is called H equal PW divide rho GQ and equal bracket U2 VT2 minus U1 VT1 close bracket divided by gravity, where the R1 and R2 are the diameter of the impeller at the inlet and outlet respectively, and for the U1 and U2 are the absolute velocity of the impeller at the inlet and outlet respectively, and for VT1 and VT2 are the tangential velocity of the flow at the inlet and outlet respectively. As we can see at the picture, the left side of this slide is the Euler turbo-machine equation. So, Euler turbo-machine equation can be used to predict the impact of the changing that impeller geometry on the head. It does not matter when we deal with a pump or with a turbine. If torque and angular velocity are of like sign, work is being done on the fluid, a pump or compressor. If torque and angular velocity are of like sign, work is being done on the fluid, a pump or compressor. If torque and angular velocity are of opposite sign, work is being extracted from the fluid, a turbine. For the design aspect of the turbine and pumps, the Euler equation are extremely useful.
So, our group chose the frame-mounted and suction pump. With a frame-mounted and suction pump, the pump does include a complete mechanical assembly and is coupled to a driver, both of which are mounted on a shaft base plate. The most common centrifugal pump design is the end suction pump. This type of pump combines a volute casing with a variety of impeller designs. Most typically, a radial flow impeller would be used, but in certain specialty applications, Francis Wayne or mixed flow impellers may be used. Specialty designs are often fit with unique impeller designs, allowing end suction pumps to be used in solids handling applications such as pumping municipal and industrial wastewater. One particularly popular specialty end suction design is the submersible pump. The submersible pump is an end suction design that has been fit with a motor designed to operate while submerged. This allows the entire pump to be submerged in the liquid being pumped. End suction pumps, such as the submersible, which have been designed to handle solids, are often fit with mixed flow impellers or specialty impellers such as the vortex or screw impeller. These specialty impellers are designed to handle solids without clogging. Some manufacturers offer a standardized line of end suction pumps referred to as ANSI end suction pumps. This type of pumps are built to a common set of design standards and are even dimensionally interchangeable between manufacturers. End suction centrifugal pumps are particularly popular because they offer a compelling combination of comparatively low upfront costs, acceptable service life, good efficiencies, and design flexibilities. Okay, next, the usage of the frame-mounted end suction pump. End suction pumps are used in a large range of applications. Standard end suction pumps are commonly used in fire suppression, plumbing, HVAC, and municipal water pumping applications. Specialty designs are often used in wastewater, pulp and paper, chemical, oil and gas, and a variety of other industrial applications.